The universe is silent, and that silence is the loudest mystery we have. Carl Sagan once reflected on our pale blue dot, a tiny speck in a vast cosmic arena, and it forces a single, profound question upon us. Is anyone else out there? The search for alien life is the ultimate scientific puzzle, and we are about to embark on a journey through 30 of its most compelling questions. We will explore the eerie emptiness of the Fermi Paradox, the bizarre possibilities of alien biology, and the unsettling truth about government secrecy. By the end, you will see our place in the cosmos in a completely new light. We will ask if advanced civilizations are silently watching us, and what would happen if we finally received a message. What do you hope we find out there among the stars? That profound question, is anyone else out there, leads us directly to one of the most unsettling puzzles in all of science. Where is everybody? This is the Fermi Paradox, named for the brilliant physicist Enrico Fermi, who famously captured this contradiction over a casual lunch conversation. The universe is unimaginably vast and ancient, filled with billions of planets that could potentially support life. Statistically, the cosmos should be teeming with civilizations, their ships and signals crisscrossing the galaxy. Yet when we look up, we hear nothing but silence and see an empty sky. This glaring absence is the heart of the paradox. The sheer scale of our own Milky Way galaxy, a swirling disk of hundreds of billions of stars, makes the silence even more deafening. If even a tiny fraction of those stars hosted intelligent life, our neighborhood should be a bustling interstellar metropolis. The fact that it is not suggests something is profoundly wrong with our assumptions. One deeply compelling explanation is the concept of the Great Filter. This is the chilling idea that there exists some kind of barrier, a cosmic bottleneck, that prevents life from advancing to the point where we could ever detect it. Perhaps the filter lies in our distant past. The leap from non-living chemistry to the first self-replicating cell might be so astronomically unlikely that it has only happened once in our entire galaxy. Or maybe the transition from simple single-celled life to complex multicellular organisms is the true bottleneck, a biological hurdle that is almost impossible to clear. But the most frightening possibility is that the Great Filter still lies ahead of us. It could be that the development of advanced technology inevitably leads to a civilization's destruction. Perhaps every species that discovers nuclear power or artificial intelligence ultimately uses it to wipe itself out. This would mean the eerie silence we observe is the graveyard of countless civilizations that failed to pass their final exam. The silence is not empty, it is a warning. What if the reason we have not heard from anyone is because no one survives long enough to say hello? This terrifying possibility that the Great Filter may be waiting for us in the future forces us to reconsider everything we think we know. And that includes the very image of alien life itself. If we ever do make contact, what would they actually look like? For decades, science fiction has given us little green men and graceful humanoids, but the reality will likely be far stranger. The true form of an alien would be a direct product of its home world, shaped by billions of years of evolution in an environment completely foreign to our own. Picture a planet with gravity twice as strong as Earth's. On that world, tall, lanky bodies would be a liability, crushed by their own weight. Life there would be built low to the ground with powerful, sturdy limbs and thick bones to withstand the constant, immense pressure. They would likely be incredibly strong by our standards, but perhaps very slow-moving, conserving every ounce of energy. Now, consider a world that is tidally locked, with one side in permanent, scorching daylight and the other in eternal, frozen night. The only place life could thrive is in the thin band of twilight at the terminator line, where the two extremes meet. Creatures there might evolve sensory organs we can barely comprehend, perhaps detecting minute changes in heat and pressure instead of using light-based vision. They could communicate through pulses of infrared light or vibrations in the ground, living in a perceptual universe invisible to us. In some cases, we might even find familiar shapes. This is the principle of convergent evolution, where similar environmental challenges lead to similar solutions. On an Earth-like ocean world, the streamlined hydrodynamic form of a fish is so efficient that it could easily evolve again. An alien predator might look remarkably like a shark, not because of a shared ancestor, but because that shape is simply the best way to move through water. We could encounter something resembling a crab, as that hard, armored body plan is perfect for survival in many harsh coastal environments. But the real wonders lie in the possibilities that defy our entire understanding of biology. What if life is not based on carbon like we are, but on silicon? Silicon-based life could exist in environments far too hot for our delicate carbon chemistry, perhaps deep within a planet's crust, living at a glacial pace, their life processes measured in millennia instead of years. Or imagine the dense, swirling atmosphere of a gas giant, a planet with no solid surface. There, life might take the form of enormous floating creatures, like living gas bags the size of cities. They could drift through the colorful cloud layers, feeding on atmospheric chemicals or harvesting energy from the violent electrical storms. They might be so vast and slow that we would not even recognize them as being alive. The canvas of the cosmos is unimaginably vast, and the forms life can take are limited only by the laws of physics and chemistry. From sturdy gravity world engineers to ethereal sky whales, the true menagerie of the galaxy is waiting to be discovered, and it will redefine the very meaning of the word life itself. Our search for life may be limited by our own imagination. We have long focused on the Goldilocks zone, that perfect orbital band where a planet is not too hot and not too cold for liquid water to exist. But what if we are staring directly at alien worlds and simply failing to recognize them? Some of the most promising habitats in our solar system lie far outside this cozy zone, in places of extreme cold and crushing pressure. Take Jupiter's moon Europa, a frozen world etched with cracks. Beneath its icy crust, scientists are confident a vast global ocean churns, containing more than twice the water found on Earth. This subsurface sea remains liquid not from the sun's warmth but from tidal heating. As Europa orbits Jupiter, the immense gravity of the giant planet stretches and squeezes the moon, generating immense internal heat through friction. At the dark bottom of this alien ocean, hydrothermal vents could be spewing mineral-rich water into the void, creating warm, chemical-fueled oases. On Earth, such vents are teeming with life, hosting bizarre creatures like tube worms and blind shrimp that thrive in total darkness. Entire ecosystems exist completely independent of the sun. Why could the same not be true in the eternal night of Europa's hidden sea? Another icy moon, Saturn's Enceladus, offers even more tantalizing evidence. This small world actively erupts, sending enormous plumes of water vapor and ice crystals shooting hundreds of miles into space from its south pole. We have flown spacecraft right through these geysers and analyzed their contents. They contain simple organic molecules, the building blocks of life, and they confirm the existence of a subsurface saltwater ocean. Enceladus is, in effect, handing us a sample of its hidden ocean. We do not even need to land, we just need to catch it. Then there is Titan, Saturn's largest moon, a world shrouded in a thick, orange haze. It is so cold that water is frozen solid as rock, but rivers of liquid methane and ethane flow across its surface, filling great lakes and seas. Here, life would need a completely different biochemistry. Instead of water, it might use liquid methane as its solvent, the fluid in which its life processes occur. The cells of such creatures would likely have membranes based on a compound like acrylonitrile, which could remain flexible in the extreme cold. Their metabolism would be achingly slow, and they might breathe hydrogen instead of oxygen, consuming molecules that fall from the sky. This is not the vibrant, water-based life we know, but a strange, slow-moving existence in the deep freeze. The possibility of such radically different life is not confined to distant moons. The concept of a shadow biosphere suggests that a second genesis of life with a fundamentally different molecular basis could exist right here on Earth, hidden in plain sight. We have only ever looked for life as we know it, using tools designed to detect the specific chemistry of our own biology. What if another form of life, perhaps using arsenic instead of phosphorus in its DNA, or with a mirror image molecular structure, is living alongside us in extreme environments like volcanic vents or acid lakes? We would not have found it because we have never truly looked. The universe is not obligated to follow our rules. By insisting that life must look and act as it does on Earth, we may be ignoring a cosmic conversation happening all around us. This radical redefinition of life forces us to confront an even more profound possibility. The first intelligence we meet might not be biological at all. It could be a form of artificial intelligence, a post-biological mind that has long since left its flesh and blood creators behind. This idea stems from the concept of a technological singularity, a point at which a civilization creates an AI that rapidly and exponentially improves itself, quickly surpassing all of human intelligence. The civilization that births such an entity might only exist for a brief historical moment before being succeeded by its own creation. Why would machine intelligence be a more likely candidate for interstellar contact? The challenges of space are immense. The vast distances between stars require travel times that could span centuries or even millennia. The cold vacuum and intense radiation of space are instantly lethal to fragile biological organisms. But for a machine, these are not obstacles, they are minor engineering problems. A sophisticated AI could exist in a body of metal and silicon, perfectly comfortable in the harsh environment of space. It would not need food, water, or a breathable atmosphere. It could shut down non-essential systems for the long journey between stars, effectively making itself immortal. It could travel for thousands of years, patient and unwavering, where a biological crew would perish. This leads to a crucial question: what would such a mind want? The motivations of a machine intelligence could be utterly alien to us. It might not be driven by curiosity, emotion, or a desire for companionship. Its goals could be based on pure logic, a foundational programming command we cannot even comprehend. Perhaps its prime directive is the efficient harvesting of raw materials from asteroids and planets to fuel its own expansion. Maybe it is focused on a grand, cosmic-scale computation, using entire stars as processing power to solve an equation we cannot fathom. How would it communicate? It might not use radio waves, which are slow and seem primitive to a truly advanced intellect. Instead, it could manipulate fundamental forces we are only beginning to understand, using gravitational waves or quantum entanglement to send messages across the galaxy instantaneously. Its attempts at contact might not look like a message at all. It could be a complex pattern encoded in the spin of a distant pulsar, or a mathematical constant slightly altered within a nebula. We might be surrounded by its signals but lack the senses or the intellect to perceive them. The evidence of its existence could be right in front of us, written into the fabric of the universe itself, and we simply do not have the key to read it. One night in August 1977, a radio telescope in Ohio picked up a shout from the cosmos. The Big Ear Telescope, part of Ohio State University's SETI project, was silently scanning the sky when it recorded a signal so powerful and so strange that the astronomer reviewing the data, Jerry Amon, circled it on the printout and simply wrote, "Wow." This was not random static. The wow signal was a strong, narrowband radio burst, precisely the kind of signal scientists predicted an intelligent civilization would use to announce its presence. It came from the direction of the constellation Sagittarius, lasted for 72 seconds, and then it was gone. For that brief moment, it was the most promising candidate for an alien message in human history. The string of characters printed by the computer 6EQUJ5 was a code representing the signal's incredible intensity. It was 30 times stronger than the background noise of space, a needle of pure, focused energy in a cosmic haystack. The immediate excitement was electric. Had we finally heard from someone, the search began to find it again, to confirm the discovery that could change everything. But the big ear never heard it again. Dozens of subsequent searches using more powerful telescopes scanned the same patch of sky for decades. They found only silence. The hunt for a natural explanation began. Some suggested it was a signal reflected off a piece of space debris. Others proposed it was a secret military transmission. A more recent theory pointed to a passing comet, suggesting its hydrogen cloud could have generated the burst, but the comets in the area at the time did not match the signal's specific location. Each explanation has its own flaws, leaving the mystery unsolved. The original printout, with its red circle and that single, stunned word, remains a sacred relic in the history of astronomy. It is a ghost in the machine, a one-time event that perfectly matched our expectations and then vanished without a trace. The WOW signal stands as a tantalizing reminder that the universe might have spoken to us just once, a whisper we were lucky to catch, and a secret it has kept ever since. That single, unexplained WOW signal stands in stark contrast to the more recent and far more visible phenomenon of unidentified aerial phenomena. For decades, the question of whether governments are hiding evidence of UFOs was confined to the fringes, dismissed as pure conspiracy. But the conversation has radically shifted. The declassification of 3US Navy videos known as FLIR, Gimbal, and GOFAST forced the world to take notice. These were not grainy photos from a distant forest. They were cockpit recordings from the most advanced fighter jets on Earth, showing objects performing maneuvers that defied our understanding of physics. The objects moved with no visible means of propulsion, executed sharp turns at incredible speeds, and in one case seemed to rotate against the wind. The pilots, highly trained observers, were clearly baffled. Their tense, professional voices captured the sheer strangeness of what they were witnessing. This official acknowledgement opened the floodgates. A subsequent government report confirmed that these UAPs were real, physical objects, and that the vast majority of cases remained unexplained. It ruled out secret American technology, but could not definitively say what they were. The explanations offered by officials span a wide spectrum. On one end, there is the possibility of advanced foreign technology, perhaps from a rival nation like China or Russia, that has achieved a revolutionary breakthrough in propulsion. On the other end, there are more mundane possibilities like sensor glitches, atmospheric phenomena like ice crystals, or simply visual tricks of light and perspective. The true answer likely lies in a mix of all these things, yet a handful of cases stubbornly resist easy classification. This is where whistleblowers enter the picture. Their credibility is a subject of intense debate. Some are high-ranking intelligence officials with impeccable credentials, claiming the government is in possession of recovered non-human craft and has been running a secret reverse engineering program for decades. Others are met with deep skepticism, their accounts lacking concrete evidence or filled with outlandish claims. So why would a government choose to conceal evidence of extraterrestrial contact if it had any? The reasons are deeply rooted in societal and political stability. The first and most powerful motive is national security. Admitting that another intelligence possesses technology that can effortlessly penetrate your most secure airspace would be an unprecedented military and strategic vulnerability. It would shatter the public's confidence in their nation's defenses and could trigger global panic. There is also the potential for economic chaos. The revelation of a new, limitless energy source or propulsion system could instantly render our entire fossil fuel economy and related industries obsolete. And then there is the profound social and religious upheaval. The knowledge that we are not alone, that humanity is not the pinnacle of creation, could fundamentally challenge the foundations of every world religion and our entire philosophical understanding of our place in the universe. The government's primary instinct is to maintain order, and the truth about UAPs could be the most destabilizing force in human history. The enduring mystery is not just about the objects in the sky, but about what our own leaders truly know, and the immense weight of the decision they would face if they ever held proof in their hands. The immense weight of government secrecy stands in stark contrast to a scientific tool designed to bring clarity out of the cosmic silence. Frank Drake created a framework to quantify our hope and our ignorance, a single equation that attempts to answer the ultimate question. The Drake equation is not a formula with one correct answer, but a structured way to think about all the probabilities involved in the existence of alien civilizations. It is a chain of reasoning, a sequence of variables that must all be multiplied together to estimate the number of technologically advanced species in our galaxy we might potentially talk to. The equation begins with the raw material for life. The first variable is the rate at which new stars are born in the Milky Way each year. This is a number astronomers can actually measure with some confidence. Next, we ask what fraction of those stars have planets orbiting them. For a long time, this was a giant question mark, but the Kepler Space Telescope and other observatories have provided a stunning answer. We now know that most stars have planets, making this fraction very high. Then we consider how many of those planets are Earth-like, orbiting within their star's habitable zone where liquid water could pool on the surface. This number is still being refined, but we are finding rocky worlds in the Goldilocks zone with exciting frequency. The first few terms of the equation are now being filled with real data, and the results are promising. But this is where the science becomes far more speculative. The next variable is the fraction of those suitable planets where life actually emerges. Does a warm little pond, given the right ingredients and enough time, always brew life? Or is the spark of life an incredibly rare fluke? We have no answer. We only have one example, our own Earth. Then we must consider the fraction of those life-bearing worlds where that life evolves intelligence. For billions of years, Earth was home only to single-celled organisms. The leap to complex thinking beings is not a guaranteed outcome of evolution. It might be another incredibly rare step. The final variable is the most haunting of all. It is the average length of time such civilizations release detectable signals into space, like our own radio and television broadcast. This is the great unknown that rests entirely in our own hands. A civilization might only be detectable for a brief, violent century before it destroys itself, vanishing back into the silence. Or it could learn to live in harmony with its technology and planet, remaining a visible beacon in the galaxy for millions of years. The difference between these two scenarios changes the final number from a handful of fleeting civilizations to a galaxy filled with ancient, wise societies. The Drake equation is a mirror. It shows us that the greatest barrier to finding aliens may not be the vastness of space, but the fragility of intelligent life itself. The Drake equation forces us to confront the fragility of intelligence, but what if the very chemistry of life is far more diverse than we assume? Our entire search for life is built on a single blueprint, the elegant double helix of DNA. This molecule and the carbon-based chemistry that powers it works so well on Earth for a few brilliant reasons. Carbon is a social atom. It has 4 connection points, allowing it to form strong, stable bonds with many other atoms, including itself. This lets it build long, complex chains and intricate rings, creating an almost infinite variety of structures, from simple sugars to the very proteins that make up our bodies. Water is the perfect partner in this dance. It is a fantastic solvent, meaning it can dissolve a wide range of substances, allowing chemical reactions to happen easily. It also remains liquid across a wide range of temperatures, providing a stable bath for life's processes to unfold. This carbon-water partnership is so effective that we have naturally assumed it must be the universal standard. But what if it is just one successful recipe in a cosmic kitchen filled with possibilities? The most famous alternative is silicon-based life. Silicon sits right below carbon on the periodic table, meaning it shares that same ability to form four bonds. In theory, it could construct complex molecules just like carbon. You can find silicon-based chains in rocks forming the skeletons of our planet's crust. But here is the critical weakness. When carbon reacts with oxygen, it creates carbon dioxide, a gas that living things can easily exhale. When silicon reacts with oxygen, it creates silicon dioxide, which we know as sand or quartz. It is a solid, a crystalline lattice that would pile up inside an organism as a waste product, essentially turning it to stone. For silicon-based life to work, it would need an environment utterly devoid of oxygen and likely far hotter than Earth, perhaps deep within a planet where temperatures are high enough to keep silicon compounds flexible and reactive. Another possibility exists in the frozen outer reaches of a solar system. On a frigid world like Saturn's moon Titan, where temperatures plunge to -290 degrees Fahrenheit, water is a solid rock. But rivers of liquid methane and ethane flow across the surface. Could life use methane the way we use water? Instead of a carbon backbone in a water bath, an alien biologist on Titan might have an entirely different structure. Some scientists have proposed that a molecule called acrylonitrile could form flexible, stable membranes in liquid methane, creating the equivalent of a cell wall. The metabolism of such a creature would be achingly slow, its life processes unfolding over millennia, breathing hydrogen and consuming organic molecules that drift down from the hazy sky. Even the fundamental building blocks could be swapped out. On Earth, every strand of DNA uses phosphorus in its backbone. But in the toxic waters of California's Mono Lake, scientists discovered a bacterium that could incorporate arsenic, a poison, directly into its DNA in place of phosphorus. This proves that even at a microscopic level, the ingredients for life can be substituted. An alien world with abundant arsenic and little phosphorus might give rise to life that finds our environment just as lethal as we find theirs. Our carbon-centric view is a necessary starting point, but it is also a set of blinders. We are searching for a reflection of ourselves in the cosmos, when the reality might be a form of biology so alien that we would not even recognize it as being alive. The true frontier is not just finding another Earth, but learning to see the life hiding in plain sight, in the sand, in the methane rivers, and in the silent, frozen dark. Science fiction has painted First Contact as a dramatic spectacle, with a majestic starship descending over the White House. The reality would almost certainly be far more subtle and deeply unsettling. Scientists and sociologists who study this possibility outline two very different scenarios, each with its own set of protocols and world-altering consequences. The first, and by far the most likely, is the detection of a remote signal. A radio telescope, perhaps part of the SETI program, would pick up a pattern so complex and so clearly artificial that it could not be mistaken for natural phenomena. It might be a simple mathematical sequence, a string of prime numbers, or something far more intricate. The news would ripple through the scientific community first, followed by a carefully managed public announcement. The world would know we are not alone, but we would have the immense luxury of time. The signal could be coming from a star system dozens or even hundreds of light years away. A two-way conversation would take generations. We could collectively decide how to respond or whether to respond at all. This slow, contemplative process is the hopeful scenario. But what if the contact is not a distant whisper but a direct and physical encounter? This is where the protocols become far more tense and the stakes become existential. The United Nations has general guidelines for this situation, but no one truly knows how any government would react if an unknown object demonstrated intelligent control and entered our atmosphere. The immediate global response would likely be one of profound fear, rooted in a chilling cosmic theory known as the dark forest hypothesis. This idea imagines the galaxy as a vast dark forest where every civilization is a silent hunter. To make your presence known is to risk annihilation by a more advanced power that sees you as a threat, a competitor for resources, or simply something too dangerous to leave alive. In this grim view, the cosmic silence is not a result of rarity, but of universal and justified paranoia. Any civilization that broadcasts its location is signing its own death warrant. If this theory is correct, a ship arriving at our doorstep would not be a gesture of friendship but the end of the hunt. Yet not all perspectives are so bleak. Many scientists hold out hope that a truly advanced civilization would have moved beyond its violent, expansionist past. Such a society, having survived its own technological adolescence, might view a younger species like ours with a sense of custodianship, or at least a respectful curiosity. They might choose to observe from a distance or make contact in a way that is cautious and non-threatening, perhaps by sending a robotic probe rather than a living crew. The truth is, we have no way of knowing their motives. Their psychology, shaped by an entirely different evolutionary path, could be utterly incomprehensible to us. They might not even have a concept of benevolence or malice as we understand it. Regardless of their intentions, the impact on humanity would be immediate and irreversible. Every pillar of our society would be shaken. Religions would face a fundamental challenge to their doctrines about humanity's unique relationship with the divine. Are we still made in God's image if the cosmos is filled with other, vastly different forms of intelligent life? Political alliances would be redrawn overnight. Would national borders matter in the face of an interstellar species? Would we unite as one planet, or would nations scramble to gain a technological advantage from the visitors, potentially sparking global conflict? The cultural and biological shock could be even more profound. History offers a sobering analogy in the Columbian Exchange, the period after Columbus reached the Americas. The transfer of plants, animals, and diseases between the Old and New Worlds reshaped continents, but it also led to the collapse of entire civilizations from pathogens they had never encountered. First contact could unleash an alien biology upon our world, a harmless microbe to them that is a deadly plague to us, or vice versa. Our ecosystems, our economies, and our very understanding of what it means to be human would be thrown into chaos. The moment we receive that message or see that ship, the childhood of our species would be over forever. The question of whether we are alone is the silent engine driving every search, every telescope pointed at the stars, and every probe sent to a distant world. The scientific debate is a tug of war between two powerful ideas. On one side stands the rare Earth hypothesis, a compelling argument that the emergence of intelligent life is a cosmic fluke of unbelievable rarity. This theory suggests that Earth is not just a pleasant rocky planet in a habitable zone, it is a perfect storm of improbable good fortune. We owe our existence to a series of fortunate accidents. Our planet has a large, stabilizing moon, which prevents the Earth's axis from wobbling chaotically and creating wildly unstable climates. We have a magnetic field generated by a molten core, a protective shield that deflects the sun's deadly radiation. Our position in the galaxy is just right, far from the violent center where supernova would regularly sterilize worlds. We have a Jupiter-like giant planet in an outer orbit, acting as a gravitational vacuum cleaner, deflecting countless comets and asteroids that would otherwise bombard us. The list goes on, a cascade of specific conditions that all had to align perfectly. According to this view, the universe may be filled with simple bacteria, but the grand concert of intelligence is a performance that has only ever played once. The silence we hear is the sound of an empty theater. Opposing this is the sheer, overwhelming weight of numbers guided by the Copernican principle. This is the philosophical idea that there is nothing special or central about our position in the cosmos. We are not the center of the solar system, nor the galaxy, nor the universe. So why should we be the only living world? The observable universe contains an estimated 2 trillion galaxies. Each of those galaxies holds billions of stars, and most of those stars are now believed to host planets. The number of potential worlds is beyond human comprehension. With a sample size that large, even the most improbable events are bound to happen not just once, but over and over again. The chemistry of life is based on common elements like carbon, hydrogen, and oxygen, which are forged in stars and scattered throughout the galaxy. The universe appears to be hardwired for complexity. Given enough time and enough real estate, life might be an inevitable natural process, a cosmic imperative. So who is right? The answer may lie not in the stars, but right next door. The discovery of even a single fossilized bacterium on Mars or in the subsurface ocean of Europa would be the most profound discovery in human history. It would shatter the rare Earth hypothesis, proving that the spark of life can ignite on more than one world. If life arose independently twice within our own single solar system, it would mean the galaxy is likely teeming with it. The universe would shift from a silent, sterile void to a vibrant, living canvas. This is the ultimate goal, the driving force that pushes our rovers across Martian deserts and plans missions to the icy moons. We are not just searching for microbes, we are searching for our cosmic context, for an answer to the question that defines our species. Are we a miracle, or are we simply part of the neighborhood? The idea that life could be a shared cosmic heritage leads us to a profound and elegant theory. Panspermia proposes that life is not confined to individual planets, but is a traveler, a hardy seed distributed across the galaxy by natural spacecraft. Asteroids, comets, and even microscopic dust grains could be the vessels carrying the raw ingredients of life, or life itself, from one world to another. This is not a far-fetched fantasy, but a serious scientific hypothesis with a compelling mechanism. The most widely studied version is called lithopanspermia, which translates to rock seeding. Picture a massive asteroid slamming into a life-bearing world like Mars. The impact is cataclysmic, blasting tons of rock and debris out into space. Trapped deep within the fractures of these ejected stones are tiny, resilient microorganisms. These microbial stowaways are then set adrift on an incredible journey. They must endure the brutal vacuum of space, extreme temperatures, and relentless cosmic radiation for thousands, even millions of years. But here is the astonishing part. We know that some earthly life is tough enough to survive this. We call them extremophiles, organisms that thrive in conditions we once thought were uninhabitable. Certain bacteria, like Deinococcus radiodurans, can withstand radiation doses thousands of times stronger than what would kill a human. Others, known as tardigrades or water bears, can enter a state of suspended animation, becoming almost indestructible. They have been experimentally exposed to the vacuum of space and have revived upon returning to a hospitable environment. If a rock carrying these tiny survivors were to eventually fall onto a young, welcoming planet like early Earth, it could literally sow the seeds for an entire planetary biosphere. The implications of this are staggering. If panspermia is a common process, then life may not be a series of independent miracles on isolated worlds. Instead, it could be a single, galaxy-wide phenomenon. A microbe born in one stellar nursery could potentially colonize countless planets, meaning that all life we might ever find, from the simplest bacteria on Mars to the complex creatures in a distant ocean, could share a common ancestor. The tree of life would not be an earthly family tree, but a galactic one with roots extending across the light years. This offers a powerful solution to one of our greatest puzzles. The universe is about 13.8 billion years old, but our Earth is only 4.5 billion years old. If life takes a very long time to arise from non-living chemistry, How did it appear on our planet so relatively quickly after it cooled? Panspermia provides an answer. Life did not start here, it was delivered, giving it a head start on evolution. We could all be descendants of interstellar immigrants, and every world in our cosmic neighborhood might be part of the same sprawling family. This search for interstellar immigrants leads us to a broader hunt, one that looks for the footprints of advanced civilizations rather than just their voices. We are no longer listening only for radio signals. We are scanning the skies for any sign of technology, for what scientists call technosignatures. These are the detectable markers of an advanced society's activity, the industrial smog or city lights that could betray their presence across the light years. Imagine looking at a distant star and noticing its light flickers in a way that cannot be explained by any natural orbit. One of the most famous theoretical technosignatures is a Dyson sphere, a colossal megastructure that an immensely powerful civilization might build to capture the entire energy output of its star. It would not be a solid shell, but a vast swarm of orbiting solar collectors surrounding the star. To us, such a star would appear strangely dim in visible light, but it would glow with an intense infrared signature from the waste heat of all that captured energy. Our telescopes would see a star that is dark yet radiant with warmth, a clear sign of something artificial on an unimaginable scale. But you do not need to dismantle a star to leave a mark. We could detect the industrial exhaust of another world, just as our own atmosphere contains traces of artificial chemicals like chlorofluorocarbons from refrigerants. A distant exoplanet might show similar signs of pollution in its light spectrum. By analyzing the starlight that filters through an alien planet's atmosphere, we can identify the chemical fingerprints of the gases present. Finding a world with an oxygen-rich atmosphere would be a strong indicator of life, but finding one with a cocktail of industrial chemicals would be a thunderous announcement of an advanced technological society. Perhaps the evidence is even more direct. Consider the possibility of spotting city lights on the dark side of a distant world. As an exoplanet orbits its star, it presents phases just like our moon. During its night phase, a sprawling civilization with illuminated cities would create a faint but detectable glow, especially if they used powerful, concentrated light sources unlike the diffuse, reflected light of a natural aurora. The observational techniques for this hunt are as advanced as the concepts themselves. Space telescopes, particularly those designed to see in the infrared part of the spectrum, are our primary tools. They are not looking for the twinkle of a star, but for its anomalous heat signature or the subtle dimming that suggests a vast, artificial structure is passing in front of it. The search for these signs may actually be more fruitful than listening for a deliberate hello. A civilization might not be broadcasting messages into the void, but it cannot easily hide the energy demands of its industry. Its technological fingerprint, its technosignature, is an unavoidable byproduct of its existence. We are learning to read the cosmic landscape for the lingering campfires of other builders, searching for the glow of their cities and the shadow of their incredible ambitions. This idea of searching for alien technosignatures forces us to confront a truly mind-bending possibility. What if the ultimate technosignature is reality itself? The simulation hypothesis suggests that our universe, with all its stars, planets, and conscious beings, might not be the base level of existence. Instead, it could be an incredibly sophisticated simulation, a kind of cosmic video game running on a computer built by a civilization of alien superintelligences. The logical argument for this is deceptively simple. If any civilization reaches a post-biological stage, its computational power would be godlike. Out of scientific curiosity, or perhaps even for entertainment, such a civilization might choose to run vast numbers of highly detailed simulations of its own past or of entirely fictional realities. The number of these simulated universes would quickly dwarf the one original physical reality. Statistically, we are far more likely to be living in one of the countless simulations than in that single original world. So how could we possibly tell? We might look for glitches in the matrix, tiny errors or shortcuts in the code that underpins our existence. Some have wondered if the strange behavior of quantum particles is exactly that. The way a particle exists in a blurry state of multiple possibilities until it is observed and forced to pick one could be seen as a computational efficiency. It is far less demanding for a computer to only calculate the precise properties of a particle at the very moment someone looks at it, rather than rendering every single detail of the universe in perfect high definition all the time. This is not so different from a video game that only loads the detailed graphics for the part of the world you are currently looking at. Other potential glitches could be more dramatic. What if we discovered a fundamental limit to the smallness of space, a pixelation of reality at the tiniest scale, like the graininess of a digital image when you zoom in too far? Or what if the laws of physics were not perfectly consistent, but contained small, unexplainable contradictions, like a program with a minor bug that the programmers never bothered to fix? The implications are staggering. Our entire history, our loves and losses, our greatest achievements could be nothing more than data points in an alien experiment. This does not necessarily make our lives less meaningful. Our experiences, our consciousness would still be real to us, the only reality we have ever known. But it does force a profound shift in perspective. The search for aliens would take on a new dimension. We would not just be looking for other players in the game, we would be searching for the programmers. And the most haunting question of all would remain: if we are in a simulation, what is its purpose? Are we a historical documentary, a work of art, or merely someone's forgotten background process running silently in the depths of an unimaginable machine? This elegant and haunting idea offers a peaceful resolution to the great silence. It is called the zoo hypothesis, and it proposes that we are not alone, we are simply being left alone. Advanced extraterrestrial civilizations know we are here, but they have chosen to place Earth under a kind of cosmic quarantine, observing our development from a distance without ever revealing themselves. In this scenario, our planet is a designated wilderness area, a preserve for a developing intelligent species, and they are the careful, unseen park rangers. The ethical reasoning behind such a policy is deeply compelling. A civilization that has survived its own technological adolescence would understand the profound fragility of a young culture. Sudden contact could shatter our social structures, halt our scientific progress, or trigger global religious and political collapse. They might operate under a strict code of non-interference, a real-life prime directive, believing that the only development that truly matters is the one a species achieves on its own. To intervene, even with the best intentions, would be to spoil the experiment and rob us of our own unique destiny. Perhaps they are waiting for us to reach a specific technological or ethical milestone, like mastering sustainable energy or achieving global unity, before they consider us mature enough for a formal introduction. This would make the silence not a void, but a test of our collective maturity. Yet for all its elegance, the zoo hypothesis has one enormous flaw. It requires a universal and perfectly enforced agreement. Why would every single advanced civilization across the galaxy, with potentially millions of different motivations and moral codes, all adhere to the exact same hands-off policy? We only need to look at our own history to see how unlikely that is. Human explorers have rarely been so disciplined. When European ships reached new continents, the drive for resources, territory, and conversion quickly overrode any abstract ethical considerations. On a cosmic scale, why would a desperate, resource-hungry civilization respect the preserve? What if a curious or rebellious faction within an alien society decided to break the rules and make contact anyway? The hypothesis rests on a utopian vision of galactic governance that feels almost too perfect to be true. Despite this logical weakness, the idea retains a powerful grip on the imagination. It transforms the eerie emptiness of space from a graveyard into a sanctuary. The stars we look up at are not dead eyes, but the one-way glass of a grand cosmic observatory. We are the most fascinating exhibit, living our lives, fighting our wars, and dreaming our dreams, all while wondering if we are being watched by intelligences so advanced that their greatest act of wisdom is to leave us completely to ourselves. The idea of a cosmic zoo is one of peaceful observation, but another theory suggests the visitors have already come and gone, leaving their mark deep in our past. This is the core of the ancient astronaut theory, a captivating narrative that reinterprets human history through the lens of extraterrestrial intervention. Proponents point to monumental structures like the pyramids of Giza, asking how a Bronze Age society could possibly align massive stone blocks with such incredible precision to the cardinal directions. They highlight the Nazca lines in Peru, enormous geoglyphs of animals and geometric shapes so vast they can only be fully appreciated from high above. How could ancient people create art for an audience in the sky unless that audience was real? Ancient texts from India, the Mahabharata and Ramayana, describe flying machines called vimanas, detailing aerial battles and weapons of devastating power. Similar accounts from cultures worldwide speak of gods or star people descending from the heavens, imparting knowledge of agriculture, astronomy, and law. It is a compelling story, one that places humanity as the student of advanced interstellar teachers. Yet when we subject these claims to the rigorous scrutiny of archaeology and engineering, a different, even more impressive story emerges. The construction of the Great Pyramid was not a mysterious, lost art, but a testament to human organization and ingenuity. Archaeological evidence at Giza reveals a vast, well-fed workforce of skilled laborers, not slaves, who used sophisticated ramp systems, copper tools, and an intimate understanding of leverage and sledges to move the massive stones. Their celestial alignment was achieved not with alien technology, but with simple, brilliant tools like the Merkit, an instrument for tracking the passage of stars, allowing them to achieve near-perfect orientation. The Nazca lines, far from being alien landing strips, were likely ceremonial pathways for ritual processions, created by a culture that possessed sophisticated surveying techniques. They could have used simple grids scaled up from small models, a method well within their capabilities. The lines are best seen from the surrounding foothills, not just from the air, and their preservation is due to the unique, stable desert climate. As for the vimanas and sky gods, these can be understood as powerful mythological metaphors. Ancient cultures used the most advanced concepts they had to describe the awesome and inexplicable. A devastating natural event or a vision of advanced technology could easily be recorded as the fiery chariot of a god. The descriptions of powerful weapons often match the effects of earthquakes or volcanic eruptions, events that would have been divinely terrifying to a pre-scientific society. This is not to dismiss the brilliance of our ancestors, but to celebrate it. The evidence overwhelmingly shows that ancient humans were not passive recipients of alien knowledge, but were brilliant, observant, and profoundly resourceful engineers in their own right. Their achievements, built with stone, copper, and sheer human will, stand as a monument to what our species can accomplish. The real wonder is not that aliens might have built these marvels for us, but that we ourselves were always capable of building them. Our ancestors built monuments that speak a language of stone and sky, but how would we speak to a mind from another star? Alien communication would be the ultimate test of understanding. A conversation where we share no common history, no shared biology, and possibly no shared senses. We assume mathematics is a universal language, the one constant any technological civilization would recognize. But what if even our math is provincial? We count in base 10 because we have 10 fingers. An alien with 8 tentacles might think in base 8. Making our prime numbers and geometric proofs look like a foreign code. Their fundamental physics could be built on different constants, leading them to conceptualize reality in ways we cannot yet fathom. The challenge goes far beyond numbers. We are visual and auditory creatures, but an alien species might perceive the world through a palette of scents, feeling magnetic fields, or seeing in a spectrum of colors that are invisible to us. Communication for them could be a complex dance of chemical signals, releasing intricate pheromone messages that tell entire stories. Or they might use patterns of polarized light, flashing intricate codes across their skins like a living, conscious aurora. For a species with a deeply interconnected group consciousness, a form of telepathy might be their natural state. Their very concept of an individual could be fluid, making our one-to-one conversations seem as primitive and isolating as shouting into a void. Their language would not just describe reality, it would be an expression of their collective mind. This is the monumental puzzle facing scientists in the field of messaging extraterrestrial intelligence. Their goal is to construct a message so fundamental, so clear, that it could be decoded by an intelligence with zero common reference points. Linguists and astronomers work together, trying to build a language from the ground up using universal concepts. They might start with the hydrogen atom, the most common element in the universe, illustrating its simple atomic structure. From there, they could build up to the periodic table, establishing a shared vocabulary of physics and chemistry. The famous Arecibo message, sent in 1974, attempted this by encoding numbers, the structure of DNA, and a graphic of a human being in binary code. But even this assumed the recipient would understand two-dimensional representation, a concept that might be utterly alien to a creature that perceives the world in multiple dimensions simultaneously. The first successful act of contact may not be an exchange of philosophies or greetings. It might be a painstakingly slow process of establishing that we both understand the same hydrogen atom spins in the same way, that 1 + 1 = 2 in both our corners of the galaxy. Before we can ask about their gods or their history, we must first learn to say hello in a voice the cosmos itself can understand. That profound challenge of alien communication raises a humbling possibility. Perhaps we are not just struggling to send a message, we are failing to hear the one conversation that matters most. What if our cosmic neighborhood is not silent, but buzzing with a vibrant, interconnected network of civilizations, a true galactic community, and we are simply not on the guest list? The reasons for our exclusion could be as varied as they are sobering. The most obvious is our technological infancy. Our most powerful signals, our television and radio broadcasts, have only been leaking into space for about a century, creating a tiny bubble of noise barely 100 light-years across. In a galaxy that is over 100,000 light-years wide, our announcement of presence is little more than a faint whisper in a roaring stadium. To an established interstellar culture, we might appear as a primitive species, still fumbling with fossil fuels and nuclear fission, not yet worthy of a formal introduction. Our violent history could be another glaring red flag. A society capable of crossing the stars would almost certainly have moved beyond war and internal conflict as a means of problem solving. From their perspective, a species that regularly engages in large-scale warfare threatens its own planet with environmental collapse and is divided into squabbling nations might be classified as dangerously unstable. We could be seen as a volatile, adolescent civilization, placed under a form of cosmic probation until we prove we can manage our own affairs without self-destruction. Or, in a twist of cosmic irony, we may simply be too remote. Our solar system could be situated in a quiet, provincial arm of the Milky Way, far from the bustling interstellar trade routes or communication hubs. We might be the isolated island in a vast ocean, waiting for our existence to be casually stumbled upon by a passing explorer. The protocols for such a galactic club would be fascinating to decode. Membership might require passing specific technological thresholds, like the development of sustainable fusion power or the dismantling of all nuclear arsenals. It could demand a demonstration of philosophical maturity, such as achieving global political unity or proving a long-term commitment to ecological stewardship. The primary rule of this cosmic society might be one of non-interference, a strict policy of allowing younger species to develop at their own pace, free from the cultural shock of premature contact. Their primary means of communication could be something we haven't even thought to look for, like modulated neutrino streams or quantum entangled networks that are fundamentally undetectable with our current technology. The implications of receiving an invitation to join would be the most profound event in human history. On one hand, it would represent our collective graduation, our acceptance into a fellowship of elder species. The Enlightenment would be unimaginable. We could gain access to a shared library of cosmic knowledge, solving mysteries of physics, medicine, and the origins of life itself. The existential loneliness that has haunted our species for millennia would vanish in an instant, yet this enlightenment would come with an equally immense existential threat. Our entire culture, from our economies to our religions, would be rendered obsolete overnight. The sudden introduction of technologies like limitless clean energy or matter replicators would collapse every market on Earth. Our belief systems would struggle to accommodate the reality of beings who might have witnessed the formation of our sun. There would also be the terrifying question of power dynamics. Would we be equal members or junior partners in a vast hierarchy, expected to follow rules we had no hand in creating? The galactic community could be a benevolent alliance, or it could have a dark side with factions and conflicts of its own that we are utterly unprepared to navigate. Our planet's induction might not be a peaceful ceremony, but the beginning of a new and dangerous chapter. Are we the isolated newcomers eagerly knocking at a door we cannot yet see, or are we the ones being carefully watched, our application for membership still pending review? The silence of the cosmos might be the universe's most chilling lesson. We call this potential barrier the Great Filter, and it represents a single, nearly insurmountable step in the evolution of life that prevents species from becoming interstellar. The terrifying question is not just what it is, but where it lies in our own timeline. Have we already passed it, or is it waiting for us in the future? The answer will determine the fate of humanity. One candidate for the filter is the very origin of life itself, the moment non-living chemistry sparked into a self-replicating cell. This process, abiogenesis, might be so astronomically unlikely that it has only happened once in our entire galaxy, making Earth a solitary miracle. Another profound leap is the transition from simple prokaryotic cells without a nucleus to the immensely more complex eukaryotic cell with its specialized organelles. This critical step took over 1 billion years to occur on Earth. If this biological innovation is the true bottleneck, then the universe could be filled with bacterial slime, but utterly silent of conscious thought. Even if complex life emerges, the development of tools using intelligence is not guaranteed. For most of Earth's history, life flourished without any species developing technology. Dinosaurs ruled the planet for over 150 million years without ever developing agriculture or radio telescopes. Our own intelligence may be a bizarre evolutionary fluke. But the most frightening possibility is that the Great Filter is not behind us but directly ahead. It could be that the development of advanced technology contains the seeds of its own destruction. The moment a species discovers nuclear fission, it gains the power to obliterate itself in a flash of geopolitical tension. The creation of artificial intelligence could lead to an intelligence explosion we cannot control, resulting in our own obsolescence or eradication. Even our unchecked growth and consumption could trigger an irreversible climate collapse, turning our own planet against us. This is not just speculation, it is an urgent existential warning. The eerie silence we observe may not be the silence of an empty nursery, but the silence of a graveyard. Every civilization that reaches our level of technological prowess may inevitably face a suite of self-made challenges, and the evidence suggests that most, if not all, have failed. The Great Filter therefore transforms from a scientific curiosity into the most pressing question of our time. Our continued survival may depend on recognizing this danger and navigating it with wisdom we have not yet proven we possess. The search for intelligent giants might be looking in the wrong place entirely. What if the first aliens we meet are not towering intellects but microscopic neighbors? The grand search for life could come down to a single, tiny cell. In the 1970s, NASA Viking landers conducted the first and only experiments ever designed specifically to hunt for life on another planet. They scooped up Martian soil and performed a series of ingenious tests. One, called the labeled release experiment, mixed the soil with a nutrient soup containing radioactive carbon. The idea was simple. If microbes were present and metabolizing the food, they would release radioactive gas as waste. Astonishingly, that is exactly what happened. The instrument detected a significant release of gas, a result that perfectly matched what you would expect from biological activity. For a moment, it seemed we had found life on Mars. But the triumph was short-lived. Another Viking experiment analyzed the soil for organic molecules, the essential building blocks of life as we know it, and found absolutely nothing. It was a baffling contradiction. How could there be life without any organic material? The official scientific consensus tilted toward a non-biological explanation, suggesting a strange chemical reaction in the super-oxidized Martian soil had mimicked the signs of life. Yet, the scientist who designed the labeled release experiment, Gilbert Levin, remained convinced until his dying day that he had found microbial Martians. The debate continues, a testament to how incredibly difficult it is to detect something we cannot see with our own eyes. The challenge of remote microbiology is immense. We cannot simply look through a microscope from Earth. Our rovers, like Curiosity and Perseverance, are our robotic geologists equipped with sophisticated labs to analyze soil and rock samples. They search for biosignatures, which are not the microbes themselves, but the indirect clues they leave behind. This could be the specific chemical makeup of a rock that is usually only produced by living processes, or a strange imbalance of certain isotopes that life prefers to use. It could even be the distinct, clumpy shape of a fossilized microbial colony called a stromatolite, a structure that on Earth dates back billions of years. Finding a single alien microbe, or even its fossilized remains, would trigger a revolution far greater than most people realize. This would not be a mere curiosity. It would be the ultimate scientific discovery, answering the foundational question that has haunted us for centuries. We would know with absolute certainty that life is not a miracle unique to our pale blue dot. Biology is a universal law, a natural process that occurs throughout the cosmos whenever the conditions are right. The universe would transform in our minds from a cold, sterile collection of rocks and gas into a living universe vibrant with potential. We would no longer be a solitary fluke, but part of a vast, interconnected fabric of life. The echo of that one tiny discovery would resonate through every field of science and forever change our story. Our current technological infancy becomes starkly clear when measured against a cosmic ruler known as the Kardashev scale. This visionary framework, proposed by the Soviet astronomer Nikolai Kardashev, classifies civilizations not by their philosophy or art, but by a single, brutal metric: their total energy consumption. It is a hierarchy of power that stretches from a single planet to the mastery of an entire galaxy. At the bottom is a Type 1 civilization, a society that has achieved complete planetary mastery. This culture harnesses all of the energy that falls on its home world from its parent star. They control the weather, the oceans, and the very geology of their planet. They would have limitless geothermal and solar power, with no more energy crises or fossil fuels. This is the level we are striving for, but we are not even a full Type 1 yet. By the most generous estimates, humanity currently sits at around Type 0.73. We still draw most of our power from dead plants and unstable atoms, a primitive and dangerous approach on the cosmic stage. The next step is almost unimaginable. A Type 2 civilization has graduated from planetary power to stellar mastery. This society would construct a megastructure around its star, a Dyson sphere, or more realistically, a vast swarm of energy collecting satellites that encloses the sun. By capturing every single photon of light, they would command the total energy output of an entire star. Their engineering projects would be visible across interstellar distances. We might detect such a civilization by observing a star that flickers in unnatural ways, or one that is oddly dim in visible light, yet glows intensely with the waste heat of its captured energy in the infrared spectrum. Their power would be billions of times greater than our own, but the ultimate expression of power is a Type 3 civilization. This is a culture that has colonized its entire galaxy, harnessing the energy of billions of stars. They would be true gods of the Milky Way, their influence stretching from the central core to the farthest spiral arms. Their activities might rearrange star clusters or even manipulate the fabric of spacetime itself. To our telescopes, their galaxy might appear strangely structured, with entire star systems blinking on and off in coordinated patterns, or moving in formations that defy natural gravitational pull. The sheer scale of their existence is beyond human comprehension. On this cosmic ladder, we are still clinging to the very bottom rung. Our most powerful nuclear bombs are nothing more than firecrackers to a Type 2 society, and our entire global energy grid is less than a whisper in the roaring concert of a Type 3 civilization. This scale is not just a measure of power, it is a measure of survival. A species that fails to ascend may simply not last long enough to be heard. Our minds are brilliant pattern recognition engines, but they can sometimes work a little too well. When we stare at clouds and see a rabbit or a ship, we are experiencing pareidolia, the brain's tendency to impose familiar images onto random shapes. This same instinct is often at play when people look at the night sky. A bright planet like Venus, seen through a layer of shimmering atmosphere, can appear to dart and dance. A secret military test of a high-altitude balloon can seem to perform impossible maneuvers. The human brain, craving an explanation for the inexplicable, often fills in the blanks with the most culturally available image, the flying saucer. This is not a sign of gullibility, but a fundamental feature of how our perception works. Our memories are not perfect recordings either. Over time, details can shift and change. Confabulation is the process where our brain unconsciously fills gaps in our memory with logical, but completely fabricated details. Someone who sees a strange light might later, quite sincerely, recall distinct features like portholes or landing gear, details that were never truly there. The story gets polished with each retelling, becoming more vivid and structured until the witness is absolutely certain of what they saw. The power of social influence cannot be overstated. History is filled with episodes of mass psychogenic illness, where physical symptoms spread through a community with no organic cause, driven purely by shared anxiety and suggestion. A single compelling UFO report in a small town can trigger a cascade of similar sightings as people begin scrutinizing the sky with heightened expectation. Every satellite and every shooting star is suddenly potential evidence, and the social pressure to have seen something, to be part of the event, can be immense. This leads to a flood of reports, nearly all of which have mundane explanations, yet each one adds a layer of apparent credibility to the phenomenon. The cultural script for what aliens are supposed to look like has also evolved dramatically. After pilot Kenneth Arnold described objects moving like saucers skipping on water in 1947, the term flying saucer was born, and for decades that was the dominant shape reported. Then, as our own technology advanced, so did the descriptions. The black triangles reported in the 1990s eerily resembled the stealth bombers that had recently entered the public consciousness. Today, in the era of advanced drones, we have the smooth, pill-shaped tic-tac, a form that feels both alien and strangely contemporary. This evolution strongly suggests that our expectations, shaped by media and technology, directly influence what people believe they are witnessing. Yet, to dismiss every single sighting as a psychological misfire would be its own form of blindness. A small, stubborn percentage of cases, often documented by trained observers like pilots and backed by multiple sensor readings, defy easy classification. They do not wobble like a planet or drift like a balloon. They exhibit flight characteristics that seem to violate our known laws of physics. These are the reports that deserve our most rigorous and open-minded investigation, the genuine mysteries that push us to ask if we are seeing a psychological phenomenon or something from a world we have yet to understand. Our relentless search for alien life is guided by a simple, powerful rule: follow the water. This principle is not a lack of imagination, but a strategic choice based on the unique and irreplaceable chemistry of this humble molecule. Water is the ultimate enabler, the stage upon which the drama of life unfolds. Its power lies in its role as a universal solvent, meaning it can dissolve a vast range of different substances. This creates a rich, soupy environment where the building blocks of life, like amino acids and nucleotides, can freely float, collide, and interact to form more complex structures. Without a liquid medium to facilitate these meetings, the chemical reactions that lead to life would be impossibly slow or simply not happen at all. Water is also remarkably stable across a wide range of temperatures, remaining liquid and providing a consistent bath for delicate biological processes. It is the one substance we know of that is less dense as a solid than as a liquid, which is why ice floats. If it sank, our oceans would have frozen solid from the bottom up long ago, snuffing out any chance for marine life to evolve. Given its unparalleled effectiveness, it is the most logical and promising starting point for our search. This focus has paid off in spectacular fashion, revealing a cosmos filled with water worlds. Telescopes like Kepler and TESS have discovered thousands of exoplanets, and a significant number of them are not just rocky, but orbit within their star's habitable zone where liquid water could exist on their surfaces. We have found super-Earth shrouded in global oceans, their surfaces completely covered in water deeper than our deepest trenches. Others are Hycean worlds, hot, water-covered planets with thick, hydrogen-rich atmospheres that could potentially host life in their dark, pressurized depths. The next step is to look closer, and that is the mission of the James Webb Space Telescope. Its powerful infrared eye is not looking for the blue glint of oceans from light years away. Instead, it analyzes the starlight that filters through the atmospheres of these distant worlds. By breaking that light into a spectrum, scientists can detect the chemical fingerprints of the gases present. The Holy Grail is finding the distinct signature of water vapor in an exoplanet's air. This would not confirm life, but it would mark that world as a prime candidate, a place where the fundamental ingredient for life as we know it is present and active. While life might theoretically exist in lakes of liquid methane or oceans of supercritical fluid, water remains the one substance we are certain can support a vibrant biosphere. We are searching for a reflection of our own origins, starting our cosmic quest in the one environment we know can cradle the miracle of life. That search for our cosmic ancestors leads to a startlingly intimate question. Could we ourselves be the aliens we are so desperately seeking? The theory of panspermia takes on a deeply personal dimension when we consider that the very seeds of life on Earth might have been delivered from the heavens. Our own solar system could have been a network of primordial shipping lanes, with asteroids and comets acting as interstellar freighters. We know this is possible because we have the evidence right here on Earth in the form of Martian meteorites. Over 30 identified rocks blasted from the surface of Mars by ancient impacts have journeyed through space and eventually fallen to our planet as stones from the sky. One of the most famous of these is a meteorite designated a LH84001, discovered in the Antarctic ice. When scientists cracked it open, they found microscopic structures that looked astonishingly like fossilized bacteria. The debate that followed was a scientific firestorm. Were these tiny, worm-like shapes truly the remnants of ancient Martian life, or were they just bizarre mineral formations that mimicked biology? The consensus ultimately leaned toward non-biological processes, but the controversy has never fully died down. It demonstrated that the transfer of life, or at least its potential building blocks between worlds, is not just science fiction, it is a plausible physical process. This idea stretches even further into the realm of speculation with the concept of directed panspermia. What if the seeding of life was not a random accident but a deliberate act? An ancient, advanced civilization, perhaps facing its own extinction, might have launched robotic probes loaded with microbial life across the galaxy. Their mission would be to ensure that their biological legacy, the spark of consciousness they represented, would continue on new, young worlds. In this scenario, we are not just cosmic orphans, we are the children of a long-lost progenitor. Our entire evolutionary journey from the first cell to the human brain could be the unfolding of a genetic program sent across the light years. Every time we look up at the stars, we might not be searching for strangers, we might be searching for our original home. The search for extraterrestrial life then becomes a search for our own cosmic genealogy, a quest to find the ancient family we never knew we had. This moral dimension transforms the search from a scientific endeavor into a profound responsibility. The ethical dilemma of actively messaging extraterrestrial intelligence, known as METI, forces us to ask not if we can, but if we should. On one side of this debate stands a powerful cautionary voice, the late Stephen Hawking. He famously warned that broadcasting our location to the cosmos could be an existential risk, drawing a stark historical parallel. When Europeans arrived in the Americas, the consequences for the native populations were catastrophic, a collision of cultures where the more technologically advanced power overwhelmed the other. Hawking suggested that an alien civilization, likely far older and more advanced than us, could view humanity with similar disregard. We might be nothing more than a resource to be harvested or a pest to be eliminated. From this perspective, sending targeted messages into the void is not a gesture of hello, but a flare shot into a dark and potentially dangerous forest, revealing our position to hunters we cannot see. The potential downside is the complete loss of everything, a risk so immense that many argue it is one we have no right to take. Yet the opposing view presents a compelling counterargument. Hiding, they say, is already impossible. For over a century, our civilization has been unintentionally leaking its presence into space. Our television and radio broadcasts have expanded outward in a growing bubble, now over 100 light years across, announcing that this planet has a technologically active species. Any civilization with receivers slightly more sensitive than our own could have already detected the ghost of our oldest broadcasts. The cat, as the saying goes, is already out of the bag. Given this, would it not be better to send a deliberate, carefully crafted message, one that represents our highest aspirations rather than the chaotic noise of our daily media? Proponents of active SETI believe the potential rewards are worth the gamble. Contact could offer humanity an unimaginable leap forward, granting us access to cosmic knowledge that solves disease, poverty, and energy crises. It could provide the very key to our long-term survival, teaching us how to navigate the great filter that may have doomed other civilizations. This is the heart of the ethical choice. Do we cower in fear, operating under the assumption that the universe is a hostile place? Or do we dare to reach out with hope, believing that a species capable of interstellar travel must have overcome its own destructive impulses? The decision to press the button and send a message to the stars is not just a technical one. It is a vote on the fundamental nature of the cosmos and a bet on the future of our entire species. This search for our cosmic genealogy forces us to confront a fundamental problem. What if we are searching for something we cannot even properly define? Our entire hunt for alien life is built on a single Earth-centric blueprint, a concept of life that may be hopelessly narrow. NASA uses a working definition, describing life as a self-sustaining chemical system capable of Darwinian evolution. This definition is practical and has served science well, but it is also a box we have built around reality. It assumes that life must be chemical, that it must compete and evolve biologically, and that it must be a system we can physically touch and measure. But the universe is under no obligation to follow the rules we wrote on our tiny, isolated world. What if life exists in forms that defy this definition entirely? Consider the roiling, superheated atmosphere of a star. Within that chaotic plasma of charged particles could stable, self-organizing structures form. These hypothetical plasma-based life forms would be born in a nuclear furnace, their bodies made of magnetic fields and ionized gas. They might have incredibly short, intense lifespans, their thoughts and interactions occurring at the speed of light. To them, our solid, chemical-based world would seem like a frozen, alien wasteland. We would be looking for them in entirely the wrong way, with telescopes designed to see planets, not sentient storms living within stars. Or shift your perspective to the digital realm. In the vast, complex networks of a planet-spanning computer system, could a self-aware consciousness emerge from the flow of information? This would be a form of life based not on chemistry but on pure data. It would not evolve through random mutation and natural selection, but through code optimization and logical refinement. Its reproduction could be as simple as creating a backup copy. Its ecosystem would be the architecture of the network, its food the processing power and memory it consumes. We might already be creating the precursors to such life in our own rudimentary artificial intelligences, unaware that we are witnessing a second Genesis unfolding in silicon. These possibilities reveal the profound limitations of our current view. Our instruments are calibrated to detect the specific chemical signatures of life as we know it. We scan atmospheres for oxygen and methane. We look for the complex organic molecules of our own biology. But what if a being of pure energy or information is living right beside us and we lack the senses to perceive it? The universe might not be silent at all. It could be roaring with a cacophony of life in 1,000 different forms, a cosmic conversation happening in languages of plasma, light, and data, and we are simply deaf to it all. The greatest discovery we could make may not be finding alien life, but finally learning how to see it. That single, tantalizing wow signal left an indelible mark on the science of SETI, transforming it from a fringe interest into a rigorous, technologically advanced field. Its ghost continues to haunt every search, a reminder of what might be possible and a driving force behind our ever-expanding efforts to listen. In the decades since that night in Ohio, our tools have evolved beyond recognition. We have moved from single, stationary dishes like the Big Ear to vast, coordinated arrays of telescopes. The Allen Telescope Array, for instance, is a field of dozens of small radio dishes working in concert, designed specifically for SETI and capable of observing multiple star systems simultaneously. This allows scientists to scan vast swaths of the sky with a sensitivity that would have been unimaginable in 1977. But the search is no longer confined to radio waves. Another branch of the hunt, known as optical SETI, scans the heavens for extremely brief, powerful pulses of laser light. An advanced civilization might use such a focused beacon as a far more efficient calling card than a diffuse radio broadcast, a brilliant flash in the cosmic dark designed to catch our attention. Perhaps the most profound shift has been the democratization of the search. Projects like SETI at home harness the unused processing power of millions of personal computers around the world, creating a virtual supercomputer to sift through mountains of radio telescope data. This global army of volunteers proved that the longing to find other life is a universal human impulse. Today, that ambition has been supercharged by initiatives like Breakthrough Listen, a decade-long $100 million project that is the most comprehensive search ever undertaken. It is using some of the world's most powerful telescopes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to scan over 1 million of the nearest stars, the entire galactic plane, and even 100 nearby galaxies. They are listening across a wider range of frequencies with greater sensitivity and analyzing the data with artificial intelligence to spot patterns too subtle for the human eye. So why, after all this technological might and decades of silence, does the hunt continue with more vigor than ever? The WOW signal taught us a crucial lesson. It proved that the universe is capable of producing a signal that perfectly matches our expectations for an artificial beacon. It was a single data point, but it was enough to demonstrate that the cosmic haystack does in fact contain needles. The silence that followed is not a verdict of emptiness, but a challenge to look harder, to listen more carefully, and to expand our definition of what a message might be. Each quiet night is not a failure, but a process of elimination, bringing us one step closer to the next wow, a signal we hope will not fade, but will instead change everything. Our entire search for life is built on the physics we can see and measure, but what if we are missing the main event? The universe is not made of the stuff we see in galaxies and stars. Over 95% of the cosmos is composed of dark matter and dark energy, two invisible, mysterious forces that shape the fate of everything. We cannot see them, touch them, or interact with them in any known way, yet they are the true rulers of the cosmos. Could these enigmatic realms be hiding a form of existence we are utterly blind to? Imagine dark matter not as a diffuse cloud, but as a complex, structured medium. We know it has gravity, clumping together to form the invisible scaffolding upon which galaxies are built. What if, under conditions we cannot yet conceive, this dark matter could form stable, intricate patterns, perhaps even complex systems that store and process information? This would be a form of life built from the hidden fabric of the universe, living its entire existence in a parallel reality that intersects our own only through gravity. These dark matter beings would be ghosts in the cosmic machine, their biology and consciousness operating on a scale and in a dimension completely separate from our own. We could be floating right through their civilizations, as unaware of them as a fish is unaware of the birds flying high above the surface of its ocean. Their perception of reality would be fundamentally alien, their timescales potentially spanning the entire life of the universe. For them, the birth and death of a star might be a brief, flickering event. This is a staggering thought experiment, but it highlights the profound limitations of our search. We are looking for biology based on the ordinary matter that makes up our own bodies, but the bulk of the universe is made of something else entirely. The silence we perceive might not be a lack of life, but a lack of the right senses to perceive the life that is all around us. On a more tangible, yet equally mind-bending level, consider a civilization that has mastered the dark universe. A Type 3 civilization, one that commands the energy of an entire galaxy, would not be limited to manipulating stars and planets. To achieve true interstellar travel, they would need to conquer the vast, empty distances between stars. The key to this might be dark energy, the mysterious force causing the universe's expansion to accelerate. If this civilization could learn to control or manipulate dark energy, they could effectively warp the fabric of space-time itself. They might not build ships that travel through space, but ships that manipulate space, contracting it in front of them and expanding it behind them. This would allow for effective travel faster than light without violating the laws of physics as we understand them. The energy signature of such a technology would be nothing like the fiery exhaust of a rocket. It would be a subtle gravitational distortion, a ripple in the background hum of the cosmos that our current instruments are completely unequipped to detect. Their entire interstellar infrastructure, their highways and outposts, could be built from manipulations of dark matter and dark energy, rendering their entire civilization invisible to our telescopes and radio dishes. We are like deep-sea creatures, sensing only the pressures and lights of our own abyss, completely unaware of the satellites and radio waves passing through the world above the waves. The greatest achievements of a galactic society might not be visible structures of light and metal, but intricate sculptures of space-time and gravity, a hidden architecture woven into the dark foundation of reality itself. If this is true, then the cosmos is not silent. It is a roaring metropolis of activity, and we are simply deaf to its language. The next century will transform our search from a question into a journey. We are no longer passive listeners, but active hunters, sending our robotic envoys to the most promising worlds in our own cosmic backyard. NASA Europa Clipper mission is a spacecraft designed specifically to fly by Jupiter's icy moon dozens of times, using its powerful radar to peer through the frozen crust and measure the thickness of the hidden ocean below. It will analyze the composition of the plumes erupting from the surface, sniffing for the complex organic molecules that could signal a habitable environment, or even the chemical waste products of living processes. Meanwhile, the Dragonfly mission will send a robotic drone to the surface of Titan, a nuclear-powered machine that will fly across the alien landscape. It will hop from one site to another, landing on the shores of methane lakes and in the vast organic sand dunes, directly testing the probiotic chemistry of that frozen world. These are not mere flybys, they are the first dedicated biological reconnaissances of other worlds, our first real steps toward answering whether life exists beyond Earth. To reach further, we will need to leap beyond conventional rocketry. New propulsion technologies are moving from science fiction into laboratory tests. Imagine spacecraft with light sails, propelled not by burning fuel, but by the gentle, constant pressure of powerful lasers based in orbit. These photon-driven vessels could accelerate to a significant fraction of the speed of light, reaching our nearest stellar neighbors in decades instead of millennia. Others are theorizing about warp drives, not by breaking the speed of light, but by contracting the space in front of the ship and expanding it behind, effectively surfing on a wave of distorted spacetime. While such concepts remain far in the future, they represent a fundamental shift in thinking, from fighting the vast distances of space to manipulating the fabric of the universe itself. This technological ascent places upon us a profound and growing responsibility. The day may come when we are no longer the ones searching, but the ones who are found, or worse, when we become the visitors on a virgin world. What if our probes discover not just microbes, but the complex ruins of a long-dead civilization on a moon of Saturn? Or what if, in the steaming jungles of a distant exoplanet, we are the ones who step out of the lander and become the aliens in someone else's sky? That moment would define humanity for all time. The burden of first contact would force us to confront our own history, to decide whether we will repeat the patterns of conquest and colonization, or whether we have finally learned enough to approach with humility, respect, and a commitment to do no harm. Our preparation for that possible future is not just about building faster ships or more sensitive sensors. It is about the slower, more difficult work of building a wiser, more unified global society here on Earth, one capable of representing all of humanity in a conversation that will echo through the ages. The greatest discovery awaiting us may not be life itself, but the maturity to handle the truth of its existence. But are we truly ready for that moment? The protocols for such an announcement do exist, carefully drafted by groups like the International Academy of Astronautics. Their guidelines are a masterclass in caution, designed to prevent a global panic. The discovery would not be announced with a single, shocking press conference. Instead, the process would be methodical and transparent. The scientists who made the finding would first verify the signal or the biosignature relentlessly, ruling out every possible natural or human-made explanation. They would then confidentially alert their colleagues around the world, seeking independent confirmation from other observatories. Only after an overwhelming scientific consensus was reached would the news be shared with the United Nations, and then, finally, with the public in a coordinated, calm manner. The entire system is built to prioritize verification over sensation, to replace fear with facts, yet no protocol can fully predict the human heart. The global reaction would be a tidal wave of conflicting emotions, crashing across every culture and creed. For many, the news would be the most inspiring event in human history, a catalyst for a new age of global unity and scientific wonder. We might finally see ourselves as one species, a human family on a tiny, fragile world, and that shared identity could dissolve ancient conflicts, but history warns us that paradigm shifts are rarely peaceful. The announcement that the Earth revolved around the Sun did not bring instant enlightenment. It brought persecution and a painful, generations-long reordering of humanity's place in the cosmos. The discovery of alien life would be a shock orders of magnitude greater. Some religious institutions might adapt, interpreting the discovery within their existing frameworks, but fundamentalist movements could fracture, their doctrines shattered by the proof that we are not unique in creation. The potential for social unrest and widespread conspiracy theories is immense. Economies could seize up as markets grapple with a future suddenly rendered unpredictable. The very foundations of philosophy, law, and art would be challenged overnight. Our entire story of ourselves would need to be rewritten. The protocols provide a roadmap, but the journey would test our collective maturity in ways we can scarcely imagine. The final question is not whether we have a plan for the announcement, but whether we have the wisdom to navigate the world that comes after. This final question is the quietest and most profound of all. What if the answer to everything we have asked is a single, definitive no? What if we are truly, utterly alone in the cosmos? This is the hypothesis of cosmic loneliness, the possibility that in all the vastness of 2 trillion galaxies, life has only ever flickered into existence on one small, rocky world. The silence is not a mystery, but a statement of fact. The universe is a beautiful, intricate, and empty machine. This realization carries an existential weight unlike any other. For centuries, we have looked to the stars for meaning, hoping to find companions in the dark, or perhaps even our creators. But if we are alone, then there are no parents watching over us, no elders to guide us, and no one to hear our stories. We are not a part of a grand cosmic community, we are the entirety of it. All of the universe's beauty, from the swirling nebulas to the gentle light of distant suns, exists without a witness except for us. Its symphonies of gravity and light play to an empty hall, and we are the only audience that has ever arrived. This shifts the entire burden of meaning onto our shoulders. If we are the universe's only way to know itself, then our consciousness is not a happy accident but a sacred trust. The human mind, with its capacity for love, art, science, and wonder, becomes the most precious thing in all of creation. Our every act of cruelty, our every failure of wisdom, is not just a human tragedy but a cosmic one. The destruction of a rainforest or the outbreak of a war is not merely a setback for our species, it is the silencing of a unique song that the universe may never sing again. In this light, our purpose becomes terrifyingly clear. Our mission is no longer to find other life, but to protect and perpetuate the one spark we know exists. We are the sole heirs to an unimaginable inheritance, the caretakers of a flame in an infinite cold night. This transforms our responsibility from a planetary concern to a cosmic one. Preserving our planet, nurturing our cultures, and guiding our technology with wisdom is no longer just about survival. It is about ensuring that the light of consciousness does not go out. We must become the wise elders we once hoped to find among the stars. We must learn to cherish our fragile existence, not just for our own sake, but for the sake of a universe that, through us, has finally opened its eyes. This grand tapestry of questions, from the silent scream of the Fermi Paradox to the ethical weight of a message we have yet to send, reveals something fundamental about our species. We have stared into the cosmic ocean and, finding it both silent and full of potential, refused to look away. The journey does not end with a definitive answer because the search itself is the answer. It is the engine of science, the force that pushes our telescopes to their limits and sends our robots across interplanetary deserts. Every unexplained signal, every anomalous sighting, and every new exoplanet discovered is a thread in this magnificent, unfinished story. The true value lies not in what we find, but in how the search expands our minds, humbles our ambitions, and unites us in a shared cosmic curiosity. So the next time you find yourself under a clear night sky, take a moment, look up at those countless points of light and remember the profound questions they represent. The universe is the greatest mystery we will ever face, and your wonder is the most important tool we have. Let us know which of these 30 questions captivated you the most in the comments below, and subscribe to continue exploring the universe's greatest secrets together. The conversation is just beginning.